make variation in the composition of the system. Very easily we can make more or less dense the materials. We can, for example, find this condition where the system's water payment could be something like 7 elements per bar for the brackish water conditions. And this is highly important because also in brackish water conditions, these membranes could be considered highly important. And what is highly important on this one, also the rejection is highly important. Having this kind of performances, or not enter into details for the moment. What is highly important in both conditions, in all the conditions, we have used also the membranes for tap water purification, giving almost 30 LMH flux on the membranes and having very nice rejection. All rejection are very low pressure, 6 bar right now, and having almost the same performances like commercial ones. Highly important, if you have compared to the 3 kinds of filtration: low pressure 6 bar, brackish water 18 bars, and seawater 65 bars. Normally we have this kind of fluxes. This incremental improvement of the permeability of the systems is huge. It's something most of the people looking in the literature, we observe 30, 45, 50% more increase in the permeability by the addition of the channels into the system. Here we have several hundreds, not only 200% more and 300% more. If you look a little bit to the permeability, our membranes, probably they are the best one working in this field. This is the field of seawater. We can manage by changing the composition to have the membranes, good membranes for the brackish water, which are surpassing, or maybe they are also the membranes which are going at these values right now. But compared to the commercial ones, they are still good. And for the tap water, normally at low pressure, these membranes are working like commercial ones, and they are not so good as seawater, but still good for the application, as we have very nice rejection and almost similar fluxes to the membranes. The advantage of the inventions is disruptive technology having this high flux for seawater, salted water with high selectivity. We have an exceptional mechanical resistance proved by theoretically, chemically robust, and also providing fluxes and selectivity even in the conditions, harsh conditions we are treating the membrane. We calculated that we have at least 12% of reduction of the energy, which is could lead to the working reduce of the pressure in desalination, or produce the same amount of bigger water under the same conditions. And also this one could have a major evolution for the new emerging smaller lower cost desalination plants. I will conclude right now. I think I convince you that in principle that this artificial water channels could represent a new paradigm into desalination, in a sense that having this kind of channeling like water exclusion mechanism and channeling activating mechanism, in principle we can imagine that we can increase the permeability of the membrane in the meantime with the selectivity, which is highly important for the system. Because normally this story started 10 years ago, around 2010, and with the first discoveries of the water channels, which it's an amazing field. Then we spend a lot of time to try to compare these systems with our natural ones, and several systems have been developed around the world. The modeling guys, they come into the field to try to explain the mechanism and the several properties. I have not time to explain in this field, but they are highly important to try to explain the structure of water under confinement. And finally, after 10 years, the people, they started to get membranes, and the first membranes have been tested under aero conditions with the performances. And this is only probably there is a lot of improvements to be done into the field, and the application will come in the future. Thank you very much, all the team, and on this side is our group more or less contributing to the world. We had very nice collaboration with Manish Kumar, with George Belfort, with Mark Baden, Susanna Nunes, and other groups around the world. There's a nice team in this field, and I will finish right now with this quote here. You have to read this one. We come all this way to explore the moon, and the most important thing is we have discovered the Earth. Thank you very much for your kind attention, and I will be happy to take some questions if you have some ones. Please unmute you, Professor Su.
Thank you, Professor Baba. Then we have one question. Is there any question? Oh, that because time limited, so there's no questions. Then thank you very much, Professor Baba, and we will turn to another speakers.
Two seconds.
Okay. Professor Barbara, you can close your PPT now. And the next speaker is Professor Peng Jiadu. He comes from Shenzhen University of China. Welcome.
Hello everyone, I'm Peng Jiadu from Shenzhen University. It is a great honor to be here to introduce our work. The topic is polyethylene separator-supported thin-film composite forward osmosis membranes for concentrating lithium-enriched brine. Lithium is an important element. It has many applications such as ceramics, pharmaceuticals, lubricants, metallurgical industries, and particularly lithium-ion batteries. Most of the exploitable lithium reserve worldwide is present in solid brines, particularly in China. In China, extraction of lithium from solid brines has become the key lithium supply. Extraction of lithium from brine consists of three main steps. First, lithium is separated and purified from complicated brine by adsorption, electrodialysis, or nanofiltration. Then the obtained lithium-enriched brine is concentrated by distillation or reverse osmosis. Finally, by adding sodium carbonate, lithium carbonate product is obtained. One of the key issues is that concentration stage to remove water from lithium-enriched brine is highly energy intensive. To largely reduce the energy cost, spontaneous forward osmosis technology has been proposed. Forward osmosis, or FO uses osmotic pressure difference between two solutions separated by a membrane as the driving force for water transport. So it is a spontaneous and low energy process. In Chinese salt lakes, there is abundant and nearly free magnesium chloride crystals or brine with saturated magnesium chloride. Saturated magnesium chloride solution has an extremely high osmotic pressure of above 1000 bar. So the saturated magnesium chloride or the brine with saturated magnesium chloride are suitable for use as draw solutions to concentrate lithium-enriched brine by FO. After FO, the diluted draw solution can be directly discharged to the system to regain the osmotic power. There isn't any negative impact to the ecological system in the FO process. So this is a very good application for FO. However, the problem is that common FO membranes show very low water flux in concentrating lithium-enriched brine. Common FO membranes are thin film composite membranes comprising a dense, ultra-thin polyamide active layer and an underlying porous spore layer, typically made of polysulfone. The structural parameter of the spore layer is usually large, resulting in severe internal concentration polarization. Internal concentration polarization reduces the osmotic pressure difference across the active layer and therefore reduces the water flux. Ideal support layers to be thin, highly porous, and low touches to minimize the structure parameter. The commercialized PE porous membrane, which is commonly used as the lithium-ion battery separator, has been recently attempted to be used as the FO membrane support. The PE membrane has a high porosity and poor connectivity, and it can be very thin. So the structure parameter of the PE support can be very low. The PE membrane has a large surface porosity of about 30%. The large surface porosity helps improve water permeability of an FO membrane by shortening the water diffusion path through the active layer. In addition, it has superior mechanical strength and chemical inertness, ensuring the stability of the FO membrane. Furthermore, the low cost of the PE support increases the commercial viability of the FO membranes. These advantages make the PE separator suitable for use as an FO membrane support. So in this study, we prepared an FO membrane supported by a PE separator and used it to concentrate the lithium-enriched brine. To improve the water permeability, treating TFC polyamide membranes with an activating solvent has been found to be a simple and effective method. Among the activating solvents, benzyl alcohol was found to greatly enhance the water permeability of an owl membrane without compromising the perm selectivity. However, the effect of solvent treatment on FO performance is not yet clarified, so in this study we evaluated the effect of benzyl alcohol treatment on the FO performance. This is the schematic diagram for the preparation of the PE-FO membrane. The pristine PE support is hydrophobic and difficult to be wetted by the aqueous phase during the interfacial polymerization. Therefore, we first hydrophilized the PE support by oxidant plasma modification. Then, by conventional interfacial polymerization, the polyamide active layer was formed on top of the plasma-treated PE support. Finally, the membrane was post-treated stepwise by benzyl alcohol and hydraulic compaction. The pristine PE support shows a highly porous structure formed by interconnection of some micron thick fibers. The membrane thickness is about 9 micrometers, significantly thinner than conventional polysulfone support. The oxidant plasma treatment dramatically improves hydrophilicity of the PE support, as evidenced by the significantly reduced water contact angle from 115 degrees to 67 degrees. After IP, an active layer with the characteristic ridge and valley morphology is formed on the treated PE support. After benzyl alcohol post-treatment, no noticeable change in the surface morphology can be observed, while after further post-treatment of hydraulic compaction, the membrane shows a different surface morphology, with flattened nodular structures stacked together. Perhaps swelling by benzyl alcohol reduces the modulus of the polyamide layer. Thus, the polyamide layer is prone to deformation when experiencing hydraulic pressure. We characterized the transport properties and structural parameters of the PE-FO membranes without and with benzyl alcohol treatment. The PE-FO membrane without benzyl alcohol treatment shows a high water permeability of 4.2 RMH. In addition, the membrane has high soil rejections of above 98% for sodium chloride, lithium chloride, and magnesium chloride. The PE support has a low structural parameter of 131 micrometers, indicating a low internal concentration polarization and a high FO water flux. The membrane subjected to benzyl alcohol treatment shows an even higher water permeability of 5.7 RMH that outperforms most commercial FO and AL membranes. Furthermore, benzyl alcohol treatment maintains the high soil rejections and increases the water-soil perm selectivities, thus overcoming the performance trade-off. This may be because there are low cross-linked, loose polyamide structures at the outermost polyamide active layer. These loose structures contribute little to separation but hamper water transport. Benzoyl alcohol treatment partially dissolves the loose polyamide structures. The water permeability is thus improved, with the rejection and salt permeability coefficient relatively constant. Another phenomenon is that structural parameter decreases from 131 micrometers to 91 micrometers after benzoyl alcohol treatment. We don't know the reason yet. One guesses that benzoyl alcohol has lower surface tension than the water. This is easier to infiltrate the PE support. After displacing benzoyl alcohol from the support pores, water can fill certain pores that are not easy to be directly wetted by water. This more fully infiltrates the support pores. We study the effect of post-treatment on FO performance. Benzoyl alcohol treatment dramatically enhances the FO water flux. This may be because benzoyl alcohol treatment partially dissolves the loose polyamide structures and swells the polyamide network, resulting in a loose and open structure. The water permeability is thus significantly increased. Additionally, benzoyl alcohol induced a decrease in the effective structure parameter as discussed in the previous slide, may also contribute to the water flux increase. However, the significant increase in water flux is accompanied by a marked decrease in the reverse salt flux selectivity, indicating a significant decrease in water salt permeselectivity. This could be explained by the permeability selectivity trade-off. Higher water permeability caused by swelling comes at the cost of decreased permeselectivity. After further post-treatment by hydraulic compaction, reverse salt flux selectivity is improved considerably relative to the BA membrane post-treated only by benzoyl alcohol. This could be explained by the significant structural densification of the polyamide network under hydraulic pressure. Benzoyl alcohol treatment reduces the modulus of the polyamide layer by increasing the chain flexibility, making it more flexible and compliant, thus more susceptible to structural densification under hydraulic compaction, resulting in notably decreased water permeability and increased permeselectivity. Unlike the significant increase in reverse salt flux selectivity, the hydraulic compaction has little impact on the water flux. This could be explained by two counteracting factors. The compaction-induced decrease in water permeability results in the decrease of FO water flux. Meanwhile, the compaction-induced decrease in salt permeability can increase the effective osmotic driving force and then increase the FO water flux. In conclusion, compared with the pristine PE FO membrane, the two-step post-treatment method of benzoyl alcohol treatment, followed by hydraulic compaction, dramatically enhances the FO water flux and the reverse salt flux selectivity. We tested the FO water flux and reverse salt flux selectivity as a function of draw solution concentration using DI water as the feed solution and sodium chloride or magnesium chloride as the draw solution. Greater draw solution concentration leads to higher FO water flux as a result of the increased osmotic driving force. The water flux in ARDS is higher than that in ARFS due to the less severe concentration polarization in ARDS. In addition, the magnesium chloride draw solution corresponds to a significantly higher reverse salt flux selectivity. This is consistent with a higher water salt permeselectivity for magnesium chloride and indicates less leakage of magnesium chloride than sodium chloride. Compared with the FO membrane reported in the literature, our membrane shows the highest FO water flux in both ARFS and ARDS orientations with a high reverse salt flux selectivity, regardless of whether the draw solution is sodium chloride or magnesium chloride. To predict the water flux in concentrating lithium-enriched brine, we developed an FO model. The FO model has the following characteristics. First, the feed solute and draw solute can be different. Second, for the lithium concentrating process, the Van 't Hoff equation greatly underestimates the osmotic pressures of saturated magnesium chloride draw solution and highly concentrated lithium chloride feed solution. So we use polynomial fitting relationships to precisely calculate the osmotic pressures. So the model is applicable to any concentration. Third, for the PE support, the structure parameter is small. So in addition to the internal concentration polarization and the external concentration polarization at the active layer, we also consider the external concentration polarization at the spore layer, which is often neglected in the literature. So the model is applicable to any structure parameter. Finally, to simplify the model, we assume zero solid permeability coefficients because the PEFO membrane has high rejections for magnesium chloride and lithium chloride. Finally, we evaluated the prepared PEFO membrane in lithium concentration using saturated magnesium chloride as draw solution and lithium chloride as the feed solution. This figure shows the FO water flux as a function of lithium chloride concentration in the ARFS and ARDS orientations. We also calculated the theoretical fluxes in both orientations using the developed FO model. The calculated fluxes closely match the experimental results, demonstrating the validity of the FO model. The FO water fluxes decreases with increasing lithium chloride concentration due to the reduction in the osmotic driving force. The prepared PEFO membrane shows a high water flux in lithium concentration. According to the simulation results, at a lithium chloride concentration up to 5 mol per liter, the FO water flux is still higher than 15 RMH in both orientations. We also compared a commercial FO membrane. It is clear from the figure that our membrane shows significantly higher water fluxes in both orientations. To conclude, we successfully prepared a PE separator-supported TFC FO membrane. The two-step post-treatment method of benzoyl alcohol treatment followed by hydraulic compaction dramatically enhanced the FO water flux and the reverse sulfide selectivity. The PEFO membrane exhibited a high water flux of 66.3 RMH and a high reverse sulfide selectivity of 5.25 liters per gram in ARDS using a 0.5 mol per liter sodium chloride as the draw solution and DI water as the feed solution. The membrane showed a high water flux in concentrated lithium enriched brine using saturated magnesium chloride as the draw solution. We developed a new FO model to accurately predict the FO water flux in lithium concentration. I would like to thank my supervisors, Professor He and Professor Liu. Thanks to the other professors and students who contributed to this work, and thank the fund support. That's all. Thanks for your attention.
Okay, thank you, Professor Jiadou. You have done excellent work on forward osmosis. But for time is up, we have to move to the next speaker. Thank you again. The next speaker is Professor Zhou Baoma, come from Shanghai Jiaotong University of China. His title is on preparation of high-performance safe-film composite polyamide membrane by electrospray interface-less polymerization. Let's welcome Professor Ma.
Machu Picchu. How many times have you been to Machu Picchu?
Machu Picchu.
Professor Ma, your voice?
Sorry.
Okay.
Can you hear me? Oh.
Yes, continue, please.
Hello, everyone. Zhou Baoma, come from Shanghai Jiaotong University. I'm a doctor student my supervisor saw. The missing is vibration of high performance thin film composite polyamide membrane by electrospray interface polymerization. Water shortage is a common problem all over the world. Due to the heavy water pollution, the quantity used water scarcity is more common. Polluted water threat human health. So the traditional water treatment cannot provide safe water. The treatment based on filtration is considered to be a better technology to obtain safe water. The nano filtration can remove such nature organic matters, especially trace organic compounds. The NF membrane generally is a thin film composite polyamide TFC membrane. This membrane are generally prepared by interfacial polymerization. Either the IP reaction occur between the in an aqueous solution and as chloride in organic solution. The IP reaction is uncontrollable, so generally a thick or roughness PA layer is formed. And due to the excess of water, the isochlorine is easy to hydrolyze. This side reaction will lead to membrane default. Another, the membrane fabricating process is not green. So some new IP structure have been developed, include the constructing interlayers or embedding nanofillers or tiny reaction conductions to provide high performance IP membrane. This strategy can inhibit the interfacial instability, but the side reaction of cell chloride cannot be avoided because of the existence of water. The electrospray assisted IP is another promising strategy for by using the high voltage. The polymerization takes place at the organic water microdroplets interface to form the PA layer. Previous study has shown that the aqueous solution phase cannot be completely evaporated, so the side reaction will also happen. In order to avoid the side reaction and inhibit the interfacial stability at the same time, we propose to use electrospray and a miscible organic solvent system to repair the PA membrane. Organic solvent without fault avoid the hydrolysis of the acid chloride and improve the membrane cross link degree. This miscible solvent system is beneficial for the special and fast spring of the monomer solution and the efficient diffusion and polymerization of the monomer. We will call this process ELP. In our experiment, the PIP was developed in the ethanol, and the DMC was developed in the hexane and acetone mixed solution. And they were electrolyzed to make the membrane. The electrolyte process meter and the monomer ratio dosage was mapped, and the filtration of the best membrane is evaluated by the salt and direct. The electrolyte process meter is important for membrane purification. You can see from the picture, when the voltage was 11 kilovolt and the tip to collector distance is 2 centimeter. The membrane had the best performance. This is because that stable current model is formed. Just like this picture. In this mode, the size distribution and the stability of droplets are the best. Monomer can contact and react effectively to lead from the complete PA layer, while the other monomer parameters such as collector routing speed or narrow traverse velocity have little effect on the membrane formation and performance. So the voltage and tip to collector distance, flow rate are the principal electrolyte process parameter. They should be have process control. From this picture, we can see the PA layer thickness had a linear relationship with the amount of spread monomer. If the monomer, the reaction leaving polymerization of the membrane thickness could. So the membrane thickness could be priced control according to the spread monomer dosage or screening time. But when the remove rate allows a minimal thickness is helpful to membrane flux. The surface of the PA layer is smooth, dense, and defect. The reason for this is that the confined reaction area and the low monomer dosage improve the heat dissipation and reduce the reaction interference. This smooth surface can help the membrane resist falling. This smooth bike surface means that the PA didn't intrude into the substrate pore. So this thin and uniform PA layer and no pore emission could effective shut the water transport dissipation. This high resolution XPS and TFR spectra show that there are unmixed group on the membrane. This result confirms that there is a chemical polymerization between the PIP and the TMC. Yeah, our organic solvent system reduces the side reaction, and it has the membrane crossing decrease. So the ERP membrane had a relative narrow pore size distribution. So the membrane have a excellent rejection for divalent salt and organic dyes. Our LRP membrane is superior to most of IP and EIP membrane. I want to next slide. The harmful solvent was replaced by a green 2-methyl solvent. The TMC was dissolved in this green solvent and to react with our polyamide to form a positive charged PA membrane. Using the green solvent can reduce harm to human body or the environment. And the ELRP is similar to additive manufacturing. And the utilization rate of the harmful chemical such as TMC in the membrane process is close to 1%, 100%. So no harmful with the liquid discharged. This SEM showed the membrane had fabricated successful. The surface is slightly rough than the PIP-based membrane. And this membrane had a high rejection for the heavy metal ions. So in conclusion, the TFCP membrane was fabricated by the ELP with a miscible solution. And this membrane showed good concentration performance. I also want to emphasize the ELP method can expand the type of the PA membrane because most of organic compounds, including big aromatic amines, are difficult to dissolve in the water, but they can dissolve in the organic solvent. In this ELP process, a lot of solvent can be used. A single or max solvent are allowed, and also think the PA membrane can fabricated by the ELP and with through a green route by using green solvent. That's all. Thank you for your attention. Attention.
You're muted, Professor Su.
Professor Chen Wang, he asks you, thank you for your presentation. He has a question. Can you compare the membrane performance of your green membrane with the traditional membrane fabricated with PIP and TMC in hexane? Thank you.
With tradition. Oh, the PIP and we didn't preparation the membrane in the traditional IP process, so we didn't compare the membrane performance.
Oh, Professor Ma, I have one question. What is the usual thickness of the membrane you prepared?
Your
Thickness of the membrane usually you prepare.
thickness.
Yeah. Oh,
Better TM.
50%, 50 nanometer. Okay, thank you very much.
Yes.
Yeah, thank you. Now, let's we move to the next hotel. Professor Barbara, please.
Thank you very much, Professor Su. Thank you very much, all of you, to be here in this session. Now it's a pleasure to introduce my co-chair colleague in this session, Professor Baowei Su, coming from Ocean University of China, and he will present two-dimensional COFs and ultra-thin interlayer built hollow fibers, nanofiltration membrane for desalination, and heavy metal wastewater treatment. Professor Su, the floor is yours. Take your time to show your presentation. Thank you.
Okay, thank you, Barbara, for your introduction. This is Professor Su from Ocean University of China. I will share you about the two different COFs as ultra interlayer to build hollow fiber membranes. This is my outline. As we know, the world is suffering from water shortage and also from the water pollution. So the most promising technology is membrane technology. Among them, nanofiltration membrane has the advantage of energy efficiency, high selectivity, and high permeability. So it's quite promising for water softening. And now both IF membrane are flashed membrane. This membrane have the loading density of up to 800 square meter per cubic meters. But for hollow fiber membrane, we know that the loading density is much higher. It can be high to 30,000 square meter per cubic meters. And so it is, if we can investigate a hollow fiber membrane, it must have a very a good potential for a membrane application. But for hollow fiber membrane, and it's similar to IF membrane and our membrane, there is also a trade-off between permeability and rejection. How to solve this problem? It is just a question. We know Professor Livingston group have proposed the concept of interlayer on 2015 by using non-stranded layer. From then on, the concept of interlayer has become a hotspot on flashed membranes. Recently, Professor Chu Yang Tang has published review papers on interlayer, and they show that interlayer can shorten the water transport pathway and enhance the confinement and enhance the absorption and release of amine monomers. And many nanomaterials can use to construct the interlayer. For example, MOFs and graphene oxide. Recently, COFs has been used for fabrication of membranes. The first one to use COFs as a selective layer while interfacial polymerization is Professor Yong Wang. He has prepared nanofiltration membrane which showed excellent dye rejections. Professor Zhi Wang's group has also done similar research work. And Professor Jiang's group has deposited COFs nanosheet with the aid of PDA as an interlayer and also prepared nanofiltration membranes. and our group has prepared TPP COF interlayer while in situ construction using interfacial reaction. And we have prepared our membrane and OSN membrane with excellent performance. But till now, most COF interlayer are mainly used for the preparation of flat sheet membranes, and there are few research works was on hollow fiber membranes. So this is the research of this work. We use PSF hollow fiber as substrate, and we use TP and TA, and while the interfacial reaction to form the COF interlayer. And then we use interfacial polymerization of PIP and TMC to produce the polyamide layer. From the FTIR, we can see that there is no difference between the COF modified substrate and the substrate, and there is also no difference between the TFN and TFC membrane. But we can see from the XPS that after the modification of the interlayer, the TFN membrane has a high composition of the amine group and a low concentration of the carboxyl group, which means the cross-linking degrees increase after the incorporation of the interlayer. This is quite similar to Yang Tang's work. We have investigated the effect of COF monomers concentrations and at the fixed PIP and TMC concentration, and we have a much lower concentration of optimal COF mono concentration of 0.02% and 0.001% for P and TP respectively. After that, we have investigated the effect of COF reaction time and concurrent time. They are 15 seconds and 3 minutes respectively. And this is the cross-sectional image of the TFC and TFN membrane. We can see from the top, the very top, the TFN membrane is rather smoother. This is the surface. We can also see the much smoother surface of TFN than TFC. And for TEM, we can see the thickness of the COF layer is about 5 nanometers because we use very low concentration for TP and PA. For the TFC membrane, the PA skin layer is about 45 nanometers, but for TFN membrane, it decreased to 20 nanometers. We have investigated the separation performance of the membrane for single shot. We can see the water performance of the sodium sulfate increase from the TFC to more than 50% of the TFN, and the reduction also increased 4%. We can also see from the reduction of sodium sulfate and magnesium sulfate that sodium sulfate is a little larger, which can be attributed to the Donan exclusion effect. But for magnesium chloride, it is much higher than sodium chloride. This can be referred to steric hindrance effect. We also investigate the separation performance for different dyes. You can see that for sulfonin T, the rejection is about 90%, which means that the molecular cutoff is about 315. The membrane prepared had very good rejection for heavy metals. All the metal we invested had more than 90% rejection. And we also have tested the long-term filtration performance of the membrane. We can see after the 140 hours operation, the water permanence and the rejection remains essentially the same, which shows the membrane has very long stable performance. We also test the anti-fouling performance, and we can see that the flux decay ratio of the TFA membrane is much smaller, but the flux recovery ratio of the TFA is much higher, which means that the TFA membrane has a better anti-fouling performance than the TFC membrane. We also test the chlorine resistance. We can see that after the more than 10,000 ppm hours, the normalized rejection and the normalized rejection is much higher, but the normalized permanence is much lower for TFN than TFC, which means the prepared TFN has much better chlorine resistance. We have a comparison of our research work with some of other research work. We can say that the rejection of ours for sodium chloride is 96%. It is reasonable, and the permanence is 86%. 86. It's also reasonable performance compared with other research work. Our work has been published on Journal of Membrane Science. Now we come to the conclusion. In our work, an ultra-thin interlayer of two-dimensional coughs was in situ formed on PSF hollow fiber substrate surface. The prepared cough interlayer TFN membranes have much thinner PA skin layer, about 20 nanometers, which is much higher, which is much thinner than the TFC membrane. And the TFA membrane has higher water permanence and high sodium sulfate rejection. The prepared cough interlayer membrane has also excellent acid alkaline resistance and chlorine resistance, as well as anti-fouling performance and long-term filtration stability. It also has a good separation performance for thiometals solutions and dye solutions. Acknowledged. Okay, thanks for your attention.
Thank you very much, Professor Su. Questions from the audience? Yeah, no questions here. I have a question. Could you estimate what is the interaction between cough and the polyamide system? Did you look at it? What the cough and polyamide interaction? Do you have an idea, or do you have some data about how this one could be managed?
Oh, very good questions. We think the interaction between the coughs and the PA layer, there might be covalent bonding, because some of the cough monomers can react with MPD. And react with MPD. So there may be chemical bonding.
Do you have proofs for this, or not yet? Did you find or no chemical characterization or something?
We have not done some characterization on this work.
Okay. As there are not other questions, thank you very much, Professor Su. And we will try to get the next presentation. But before, Professor Ma, could you unmute you, please? Could you mute you? Yep, Professor Ma, you are no muted. You can unmute, mute you. Sorry. Okay. Thank you. So the next speaker is Chen Guang from the University of Technology of Australia, and she will present inject printed high performance nanofiltration membrane for desalination. So, Chen, floor is yours.
Thank you. My name is Chen. I come from University of Technology, Sydney. Today I will give a presentation named Inkjet Printed High Performance Nanofiltration Membrane for Desalination. Here is the outline of today's presentation. First, I will give a brief introduction. Then I will introduce two research work along with their results and discussion. First, let's have a look about the inkjet printing technology. It has many advantages. For example, it has a low production cost. It is a relatively simple, fast, and scalable method. In addition, it can also precisely control the material deposition and minimize the use of deposition materials. Based on these advantages, it has already been applied in many research fields, such as sensors, electronics, catalysts, biological cells, and ceramics. Actually, the inkjet printing technology have already been used in memory field. Here, I summarized some study use the inkjet printing technology for memory modification and fabrication. In the first study, they used a printer to print MPD monomer to fabricate a TFC membrane. In the second study, they used the inkjet printing technology to print the dopamine on PVDF memory surface for the hydrophilicity modification for efficient oil and water separation. In the third study, an efficient graft polymerization method was developed by printing a twisted ionic monomer on UF membrane with subsequent UV radiation. In the last study, they print the atrazine graphene oxide on a polymeric support for highly effective water purification. Because of the uniform materials deposition with minimum use and the simple turnable and scalable process, the inkjet printing has emerged as an attractive technique in memory field. Now let's start with our first study. In this study, we use the inkjet printing to print SWCNT as interlayer for high-performance TFC nanofiltration membrane fabrication. The fabrication consists of two parts. In the first part is the inkjet printing of SWCNT on the PES membrane surface. In the second part, after the successful printing of SWCNT, we did the IP process to create a polymer layer to form the final TFC membrane. Here are the membrane characterizations of the PS membrane printed with SWCNT. It's clear that from the surface morphology of the SEM images, with the increase of SWCNT prints, the memory surface was gradually covered with SWCNT. When the prints reached 15, the memory surface was fully covered. From the AFM images, it's clear that with the increase of the SWCNT prints, the memory surface roughness decreased. Here are the SEM images of the final TFC membrane. We can see that with the increase of SWCNT interlayer prints, the TFC membrane surface becomes smoother. From the cross-section SEM images, we can see that with the increase of SWCNT prints, the active layer thickness decreases. For example, for the control membrane without SWCNT prints, the polymer layer thickness is around 123 nanometer. For the TFC memory with 20 SWCNT prints, the polymer layer thickness is around 41.7 nanometer. Next, let's see the membrane performance. The first figure is about the permit flux and salt rejunction performance of the TFC membrane with different numbers of SWCNT prints. We can see that from the 0 to 10 SWCNT prints, the TFC membrane exhibited the increased permit flux. This is because of the thinner active layer, as we shown before. However, when the prints increased to 15 and 20, the permit flux decreased. This is because of the higher degrees of cross-linking of the polyimide layer, which will create a denser active layer, leading to the decreased permit flux. So this data we didn't provide here, but you can find in our paper. In addition, we can see that with the increase of the SWCNT prints, the sodium sulfate reduction increase. The optimum condition can be found at the TP15 with 15 SWCNT interlayer prints. In this condition, the permit flux is around 18 LMH per bar with sodium sulfate reduction around 97.8. The second figure is about the membrane performance under various source as feed solution. It's clear that the TFC membrane exhibited the highest reduction to sodium sulfate, followed by the magnesium sulfate, magnesium chloride, and sodium chloride. We also did the long-term test. In this figure, it's clear that with both the permit flux and sodium sulfate reduction are stable during the operation time of 48 hours, indicating the good mechanical stability of our fabricated TFC membrane. Then let's have a summary of the first study. First, a high-performance TFC nanofiltration with extra-thin polyimide layer was successfully fabricated with printed SWCNT as interlayer. Second, the TFC membrane fabricated at optimum condition with 15 prints of SWCNT exhibited the permit flux of around 18 LMH per bar with sodium sulfate reduction around 97.8%. The TFC membrane exhibited stable water flux and salt reduction over 48 hours filtration test, indicating its good mechanical stability. Then let's have a look about our second study. In this study, we use the inkjet printing for the commercial membrane surface modification. Here is the graphical abstract of this study. First, we print the dopamine on a commercial nanofiltration membrane surface. Then we print the graphene oxide on the surface. The dopamine will self-polymerize to polydopamine, which will act as a strong binder between the polyimide layer and the graphene oxide particle. In order to have a clear view about the printing process, here we provide a video. We can see that this is a cartridge unloaded with our dopamine and graphene oxide ink separately, and this is a PS membrane. So now it is printing the chemicals on the membrane surface. Then let's move to the results and discussion part. These are the ICM images of the control and modified membrane. Compared to the control membrane, our printed membrane with the increase of PDA and geoprints, the membrane surface are gradually covered with a layer, which is more clear in the big magnification ICM images. In addition, the contact angle value decrease with the increase of PDA and geoprints, indicating the increase of the membrane surface hydrophilicity. Then let's see the membrane performance. In this figure, we can see that compared to the control membrane, our modified membrane exhibited the higher sodium chloride reduction with slightly lower permit flux. For example, compared to the control membrane, the permit flux is around 13 LMH per bar with 90% sodium sulfate reduction. For the PDA geosrin membrane, the permit flux is around 10 LMH per bar with 93% sodium sulfate reduction. Then we investigate the membrane anti-fouling property of the control and modified membrane. From this figure, we can see that compared to the control membrane, our modified membrane showed better anti-fouling property. For example, at the end of operation time of 3 hours, the normalized permit flux reduction of the control membrane is around 48%. However, for the PDA-03 membrane, it's
Yes, we
around
can
20%. Then we did the recycling test to further investigate the membrane anti-fouling and recycling property. After each filtration test, we did the cleaning with DI water. From this figure, we can see that first, both the control membrane and PDA03 membrane, the permit flux cannot be fully recovered. However, our PDA03 membrane showed better anti-fouling and recycling property compared to control membrane because of the higher normalized permit flux at the second and third cycle. Then we did the chlorine stability test of the control and modified membrane. Both of the membrane are soaking in the 6,000 ppm sodium hypochlorite solution for 1 and 3 hours. From this figure, we can see that compared to the control membrane, our modified membrane showed better and chlorine-resistant property because of the minor sodium sulfate reduction after chlorination time of 1 and 3 hours. Then let's have a summary of the second study. First, the nanofiltration test results reveal that the PDA geoprinted nanofiltration membrane exhibited higher salt reduction with lower permit flux. The PDA Geo3 printed membrane exhibited enhanced anti-fouling property. It also showed better chlorine resistance compared to the control membrane under the chlorination time of 1 and 3 hours. Next, finally, I want to thank my supervisor, Professor Shong, for his kindly support. That's all. Thank you.
Thank you, Jen. We have a question. Zhong Yao Zhu. Hi, Chen. Nice talk. Could you give some comments on the difference or advancement of print between your print method and spray coating strategy? What's the difference and the advances provided by print against spray coating?
Print and spray coating. I think our print, the main advantages of the print technology is the minimum of the use of chemical. There is it's a very little amount of the chemical used because some of the chemical, they are very expensive, like the nanomaterials. So the minimum use of chemical can save the membrane fabrication cost compared to the spray coating, because during the spray coating, we know that there are some chemicals waste during the membrane fabrication process. So I think my talk answered your question.
Okay. Other questions? No other questions on the floor. I have one. Do you? I want to ask the speed of the injet, and there is another crystal long. It's something. The question is, what is the speed of the injet?
Weight or the speed of the inkjet printing, right?
Yeah. Crystal long asking this.
Yeah, I think it depends on the printing quality. You know, there are different kind of printing quality. You can choose maximum quality, the best quality, and normal quality. In our case, if we choose the maximum quality with the highest DPI, it will take around 1 minute to finish 1 cycles of printing. But if we choose the normal quality with less DPI, it takes around 15 seconds to finish 1 cycle of printing.
Okay, I have a last question here. Did you try to use this membrane in high pressure? Or I saw usually you test the membrane in low pressure application. Did you try to use this one in high pressure?
High pressure.
What is the highest pressure are you using? You know.
Actually, highest pressure is around 10 bar. It's
Yeah, but
because
this is not high.
fabricate this membrane mainly for the nanofiltration, so we haven't tried with
Okay.
nano. Yeah.
It's okay. 10 is okay for nanofiltration.
Yeah,
Thank you. As we have not other questions, thank you very much, Chen, for this nice presentation.
Thank you.
And we'll go further for the next one, the last one into the schedule, which will be done by Chang Kun Liu from Shenzhen University, and we present preparation of forward osmosis and nanofiltration membranes for structural modification perspectives. Chang Kun, the floor is yours. Unmute you.
Excuse me, can you hear me?
No, it's okay.
Okay, so just now the slide shows a little bit problems because it cannot be expanded. So now I have expanded this, but can you see this?
Yes, it's okay. I think if you cannot expand, try to expand on this so we can see.
Okay, so can I start?
Yes.
Okay. Okay, good afternoon, ladies and gentlemen. It is a great honor to be here in this session. And my report is the preparation of the forward osmosis and nanofiltration membranes from the structural and modification perspectives. And I'm Prof. Liu Changkun in Shenzhen University, China. I will share with you 4 of our research works, and with the first 2 of the works related with the forward osmosis membranes, the FO membrane, while with the other 2, nanofiltration membrane, the NF membrane. So in the first work, we have prepared the forward osmosis membranes with the layer-by-layer structured skin layer. So we functionalized the PVDF membranes with the polydopamine first, and then after that, we will structure the skin layer while the layer-by-layer means with the reactions of the sodium alginate, the SA, and also the polyethylene imine, the PEI. So we have structured the single, 3, and 5 by layers with the reactions of the SA and the PEI. And
could you move your slides, please? You are on the first one. Try to use this format, but try to move your slides.
Move your slides. Okay.
Yeah, you are on the first one right now. Sorry.
Sorry, is it still on the first one? I will try. Sorry for the trouble. I will share with my screen again. So, can you see the slides? Excuse me, can you see the slides?
Yes, but try to move there. Yes, like this. Okay. At least, yeah.
Yeah. Just yes. Now I moved the slides, so.
It's okay.
Okay. So sorry for the trouble.
Go.
So I will start again.
Go.
Okay. So can you see the movements of the slides?
Move.
Okay, they are moving, right? Okay, thank you. So I would like to share with 4 of my research, with the first 2 related with the FO membranes and the next 2 related with the nanofiltration membranes. So in the first work, we have prepared the FO membranes with the layer-by-layer structured skin layer. And we have actually functionalized with the PVDF membranes with the polydopamine first. And then after that, we will structure the skin layer, while the means of the layer by layer with the reactions of the sodium alginate SA. And
Which slide are you presenting right now?
sorry.
Yeah, try in the meantime, try to change the slides. Click on the second or third or whatever, as we have to see in the slides, please.
Yeah, because we are.
Now you are again on the first one only.
It is okay.
What slide you have in your computer right now?
Yes, it is on the computer, and I'm moving the slides. I'm moving the slides now. So.
No. Try to. We cannot see only. We can see only the first slide.
Okay.
Try to click on the second one.
But I am now on the fourth slides. So
no. In your presentation here, let's see if I can do something for you, but I'm not sure for the moment.
Yeah, I understand that maybe you just see the first slides, but I'm now moving to the fourth to the third slide.
Yeah, Iran, maybe you can take the.
Yes. Professor Liu, if you could just try, I think you've selected the wrong window and you have your PPT open in 2 windows. So you're probably moving in another window while you're sharing the static window with us. So could you just quickly stop sharing this? And when you select share, just close all the other PPTs and just keep it open in one place.
Okay. Let me see. So
now please share, and then you can select just that one PPT that you have open. You can share screen.
So can you see? I'm sharing now.
Yes.
Yes.
So can you see the second slides?
Yeah. Now when you click, now when you clicked, we could see. So you need to ensure that you do that manual click after every slide.
Yeah, like this. Try to yeah.
I understand. I'm doing the manual slides, but when it is expanded, I also do the manuals.
Don't extend the thing. This is fine for us. So please just continue in this. Thank you.
Do like this, yeah.
Just to do it like this. But
yes.
It is smaller.
It's okay. Go. In any case, on the other side, you cannot see anything.
Okay.
It's better this one.
So I'm really sorry for the trouble.
Go.
Okay. Okay. So yeah. So we have structured the skin layer, while the layer by layer means with the reactions of the sodium alginate SA and the polyethylene imine PEI, and we have structured skin layers. We have structured a single 3 and 5 bilayers with the reactions of the SA and the PEI. And the FTR was used to prove the successful synthesize process. And it is found that with the increase of the number of the bilayers, the water's contact angles would show a steady decrease, indicating the steady increased hydrophilicity. So after the preparation, we use the materials to test about the FO performance. And we found that with the increase of the draw solution concentrations, the water flux shows the significant increase, while the reverse salt flux only shows a steady increase. And also this material has the advantage of showing high rejections for 5 of the heavy metal ions. So we further look into the mechanisms of the high rejections of the metal ions, as well as the enhanced water flux. And the skin layer is actually prepared with the PEI and SA. Well, it contains some of the residue amine groups. The amine groups can actually form the coordinations with the heavy metal ions, and so that they will increase the rejection and prevent the metal ions from penetrating the skin layer. And also the coordinated heavy metal ions would form an electrostatic repulsive force with the incoming metal ions in the solutions, further increasing the rejection. And also the coordinated heavy metal ions would combine the water molecules in the solutions which would be favorable of increasing the hydrophobicities of the surface, and which is also favoring the increase of the water flux. So in the first work, we have prepared the FO membranes with the enhanced water flux and as well as the high rejections for the heavy metal ions. And in the second work, we also prepared the FO membranes, but this time is with the porous hydrogel intermediate layer. So we use the PES supports, and on top of it, we fractionalized it with the hydrogels with the zinc oxide nanoparticles inside. And then after that, we soak these membranes in the hydrochloric acid solutions and remove the zinc oxide nanoparticles. And then we carry out the interfacial polymerizations using the MPD and TMC to form the skin layer, so that a sandwich structured forward osmosis membranes is prepared. The FTIR and XPS are used to prove the synthesized preparation, and especially we found that after we immobilize the hydrogels on top of the PES supports, we can see the zinc oxide nanoparticles. We can clearly see it, but after the soaking in the hydrochloric acid, the zinc oxide nanoparticles has been removed, leaving only the pores. So the hydrogels are quite porous. So after the preparation, we tested about the forward osmosis performance, and we found that the modified membranes shows the enhanced water flux almost 3 times of the pristine ones. And also it shows the enhanced heavy metal ion rejection. And with the increase of the concentrations of the heavy metal ions in the feed solutions, the forward osmosis membrane shows a steady decrease in the water flux, but that is natural because the osmotic pressures are lower. Well, during this process, the heavy metal ion rejections showed a steady increase. So we further investigated about the rejection mechanisms with our materials, and we found actually there are double barriers for the heavy metal ions. And one rejection barrier is the intermediate layer, which contains the residual carboxylic groups. And these carboxylic groups can actually combine the metal ions while the electrostatic attractive force. Therefore, it shows the first barrier to most of the heavy metal ions. Well, there are a few heavy metal ions which can penetrate this intermediate layer into the skin layer. And the skin layer shows the positive charge as determined by the superpotential measurements, so that it will show the electrostatic repulsive force to the heavy metal ions, forming a second barrier. So in the second work, we have prepared the forward osmosis membranes with the porous hydrogel intermediate layer, which will show the double barrier for the rejections of the heavy metal ions. So in the third work, we have prepared a novel nanofiltration membranes with the metal aminophosphonate networks. So we use the hydrolyzed polyacrylonitrile membranes, the HPAN membranes, as the substrates, and functionalize that with the aminophosphonate. And the aminophosphonate was prepared while the typical carbonate fuse reactions using the glutaraldehyde and polyethylene imine, and also the diethyl phosphide, GAPA and the DEP. So this aminophosphonate, known as the APN, can further react with the iron to form the metal aminophosphonate network, the MPN, and we can further immobilize the MPN onto these HPAN membranes to form a nanofiltration membranes. And we can see from the state potential that after this modification, the state potential shows a significant increase, showing that this membrane surface contains a lot of the positive charges. So from the SEM images, we can see that after the modification, the surface turns to be smooth. And from the cross sections, we can see that actually a skin layer was clearly formed for these nanofiltration membranes. So we tested the membranes, tested the nanofiltration performance with these membranes, and we used both the APN and MPN modified membranes to test, and used the cobalt solutions as the feed solution, and found that actually the APN membranes shows both lower rejections and for the metal ions, and also the lower water flux as compared with the MPN membranes. So we further tested about the rejections using the binary system of the metal ion solutions, and found that although the water flux shows a little bit decrease, the rejections are still higher. So we further expand the types of the heavy metal ions and found the similar good results. And we have compared our results with the results in the literature and found that our materials are superior in both the rejections of the heavy metal ions as well as the water permeability. So we make a step further by using the ion for the reactions with the ammonium bicarbonate, and to form the hydroxyl iron oxide, which shows the needle-like structure on the surface. And this kind of materials has the functions of the catalytic performance, because it can degrade the dyes with a very fast speeds and with a very high degradation efficiency. We also carry out the repeated use of these membranes, and during the 4 cycles of the degradation experiments, and after 10 minutes, the degradation efficiency all reached nearly 100%, showing a good catalytic performance. So in the third work, we have prepared the nanofiltration membranes with the metal aminophosphonate networks. And this membrane shows high rejections for the metal ions. And if we make a step further, we can actually prepare the membranes with the multifunctions, carrying both the functions of the nanofiltration membranes as well as the catalytic performance. And in the fourth work, we also prepared the nanofiltration membranes, but this time the membrane is grafted with the hyperbranched polyglycerol. So we still use the PES support, and we immobilize the carbon nanotubes while the vacuum filtration means. And after that, we carry out the interfacial polymerizations with the hyperizine PIP and also the trimethyl chloride, the TMC. And when the skin layer is formed, we functionalize the skin layers with the hyperbranched polyglycerol, the HPG, to produce nanofiltration membranes. So we have carried out the AFM test and found that actually the surface roughness is lower after this modification, indicating that it shows good anti-fouling performance. And also the water contact angle shows a significant decrease, and also it shows a faster decrease with the increase of the time, while the city potential shows a steady decrease also. So after this preparation, we utilize these membranes in the nanofiltration performance, and we found that the modified membranes shows a higher water permeance as compared with the Princeton membranes in both DI water and various source solutions. And we also tested about the anti-fouling performance using BSA, humic acids, and also the silica oxide as the model foulants. Now, we found that with all of the 3 foulants, the modified membranes shows a better performance in the anti-fouling property, especially with the HA humic acids, because the humic acid would actually pollute the surface very seriously. And it shows that the water flux, the normalized water flux after the fouling would be the 65%, and after cleaning, the water flux recovery would be 70%. So both of these results are much better than the Princeton ones, because for the Princeton one, the normalized water flux after the fouling and the flux recovery were only the 44 to 47. So the results shows that the modified membrane shows much better anti-fouling performance. And we also carry out the QCMD tests and found that actually for the modified membranes, the foulant mass increase only shows a small increasing trends. While for the Princeton membranes, it shows a significant increasing trends as the increase of the time. Yeah, so in the fourth work, we have prepared nanofiltration membranes grafted with the hyperbranched polyglycerol. And these membranes shows both the enhanced water flux as well as the good anti-fouling performance. And normally in the literature, the good anti-fouling performance was achieved with the sacrifice of the water flux, as we have to functionalize or immobilize some of the anti-fouling agents on the surface. So this work just shows the significance of the nanofiltration membrane preparation with both the increase of the water flux as well as the anti-fouling performance. Okay, thank you very much.
Any questions from the audience, please? Okay, if not, I have one. There is an important, what is the importance to how we add these additives into the membranes? In principle, when you add these additives, you add in different ways. And do you observe some different behaviors of the membrane if the additives are added differently to the membrane or not?
Sorry?
Yes.
Actually, just now, sorry, just now I cannot hear it clearly. Could you repeat?
Yeah, you add the additives, the polyethylene, the glycols and stuff like this. It is important, how important it is to add these additives in different ways. If you want, you can add on this by adding them on the surface of the membrane. You can add on the polymerization solution. Did you change a little bit this one or not?
You mean the nanofiltration membrane preparation?
Yeah.
Which work?
It doesn't matter. In general, I'm speaking.
Okay.
What is the importance of the way you add the additives to the membranes?
You mean the preparation, right?
Yeah.
Actually, we prepare such kinds of membranes with some of the, such as the nanofiltration membranes. We would like to reject the heavy metal ions, so we have to design a special surface so that it contains the functions to reject the metal ions. At the meantime, it would be there will be not much sacrifice to in the water flux. So we have to, yeah.
Okay, thank you. Other questions? If not, thank you very much again for your presentation. And please join me and Professor Su to thank all the speakers of the session. And I think we have done. There is no any more speakers into the session. Thank you very much, all of you, to be here this morning. Morning in France, sorry, this afternoon in China. Irene, do you want to say, or Professor Su, you want to say something?
Okay. Thank you very much for all the presenters. Thank you, Professor Baru. Okay,
Thank you.
that's all.
Irene?